So let's start with the linearization. Now the main idea in linearization is the following. We live on a sphere like Earth, okay, but you look around and you swear that the Earth is flat. The people on the other side of the planet in California, they again swear that the Earth is flat, and they refer to us as the people on the other side of the planet. Okay, so this is linearization. You look around and you think you are living in a flat world. So if you are on a curve, going back to calculus, if you are a point on a curve, you look around and you think you are living on a straight line. Okay, so that straight line will be approximated by the tangent line. So we write the equation of the tangent line at that point, and the values on that tangent line closely approximates the points on the curve around that point. Okay, so if you move away from that point, obviously, obviously the line starts to deviate from the curve, which is again the same situation on Earth. If you start walking away, I can see you for a long time, but after a certain time, due to the curvature of the Earth, you start melting into the horizon. I don't see you. Okay, so the same thing happens with the tangent line. So that's the idea. Now we make it formal. Okay, so we have a curve. We start with the curve. Okay, so we start with the curve y equals f of x. So instead of that curve, we consider a tangent line here. Okay, so this is the tangent line. I deliberately mix the curve and the line because that's really what happens if you are around that point. Okay, so this is the point x sub 0, some number here. So this is the tangent line. Okay, so you should all know the equation of the tangent line by heart. Okay, so y equals the slope is the derivative of the function at that point. The line passes through the point x minus x sub 0 and this point. Okay, so that's these are the coordinates of this point, x sub 0, f of x sub 0. Okay, so the equation of the tangent line. You see that this is a linear equation, very easy to write down and very easy to calculate around this point. Sometimes this function may be complicated. Okay, so if you want point-by-point approximation, that's a different thing, but this is an analytic approximation. Okay, you can easily change y, and this will give you an idea about what the function is doing around that point. Okay, so this equation for the tangent line approximates the values of f around x sub 0. Okay, so here the key word is around, because if you move too far away from x sub 0, you see here the value of the function is here. Your claimed approximation is quite different than this number. But around here, if you stay in a small neighborhood here, okay, so you look at these things, you see that the error is very small. At this point, we don't have tools to give an upper bound for the error, but next semester when we do Taylor's theorem, we will know exactly. Well, if you know exactly what the error is, you know the exact value. We will have upper bounds for the error. Okay, so I think here the upper bound will be 1/2 the second derivative, upper bound for the second derivative. But anyway, this semester we will not be interested in the upper bound. Okay, so this being the idea, so we say we consider this function. Okay, so we call it Lx to suggest linearization. Linearization of f at around around point x sub 0 is f prime x sub 0. x minus x sub 0 plus f of x sub 0 is linearization of y equals f of x around x sub 0. Okay, so that's all there is to it. So we can do a few examples. And then we talk about differentials. Again, differentials, it's again mechanical, but let's see. Okay, so an example on page here. So what is the example? Okay, let's do square root function. Okay, so example 1, f of x equals square root of x plus 3. Write an equation, write a linearization around, okay, let's say x equals 1. Okay. So, this being the problem, this is all you have to think of. You have to take the derivative of the function, evaluate it at x sub 0 equals 1, evaluate the function at x sub 0 equals 1, and write this thing. Okay? So this is geometrically the equation of the tangent line of the curve at that point. Okay, so for this thing we write f of 1. I need this. So f of 1 is 2. Okay, so we are assuming that we are taking positive square root. We calculate f prime x. F prime x is what? 1 over 2 square root 1 plus x plus 3. And we need f prime of 1. Okay, so this is 1 over 4. Okay. So we have all the numbers. That's all there is to it. Then linearization is equal to 1 over 4 x minus 1 plus 2. If you are going to use this, then you may simplify it. Okay, but this is the linearization. Okay. So is there in the some of the examples in the book require you to use calculators to calculate the exact value of this and check how this varies from this. But the idea of those examples is to give you a visual impression about what is happening. Next semester we'll know exactly how to express the error. So we are not interested in that. Useful linearizations. Okay, so what is a linearization of sine x? F of x equals sine x. Okay, so the graph of sine x is something like this. Okay, so it goes like this. Okay, so we want the linearization at this point. So you see that it looks like a straight line there. So to say that it looks like a straight line in everyday language in calculus means that the tangent line approximates it. So let us look at what is the linearization of sine x at x equals 0. Of sine x at x equals 0. Okay, f of 0 is 0. Okay, so this part will be 0. We calculate f prime x, which is cosine x. Then we calculate the value at 0. It is 1. Okay, so then we write this. Lx is equal to 1 times x minus 0 plus 0. So just x. Okay. So this is what we meant by saying this is the meaning of sine theta is approximately theta for small theta. Okay, the straight line, the straight line y equals x is something like this. Okay, so I think it goes like this. Okay, so around the origin, x behaves like this. Of course, if you move a little bit around the origin, you see that x sine x goes away from this, and sine x stays here. This straight line goes here. So if you want to approximate sine x with this linearization, you don't get anything meaningful. Okay, but if you want to find the linearization of sine x at this point, then you do the same game with a point here. Okay, let's do this for cosine x. Okay, so cosine x is the graph shifted here. So we'll be looking at this point. F of x equals cosine x. So the graph is something like this. Okay, so let's just look at this part. Okay, so at this point, the tangent is horizontal. So this is the tangent line at this point 1. So we expect the linearization to be L of x equals 1. Okay, the straight line y equals 1 approximates, is a tangent line to the curve, so it approximates the curve. Let us check if algebra will also give the same thing. F of 0 is 1. So the question is linearization at x equals 0. F of 0 is 1. F prime x is sine x. F prime 0 is 0. So Lx is 0 times x plus 1, as expected. Okay, so other useful linearization is, okay, tangent x. Minus where? Okay, minus sine x. Okay, so let's take the derivative of tangent x correctly this time. Tangent x. Okay, so tangent x, again, first we develop a feeling for this. So the graph of tangent x is something like this. Okay, so here you see that, again, you expect a straight line to be tangent. That's going to be the slope of tangent at that point. We know that the tangent derivative of tangent is secant square. At 0, it is 1. So it will behave like this one. Okay, so f of 0 is 0. Okay, f prime x is secant square x. F prime 0 is 1. So linearization is derivative times x minus 0, x plus this value. Okay, Lx equals x. So it's the same linearization as sine x, which is not surprising because, well, next semester we'll see an explanation for these things. Maybe today I can talk about a little bit for the next terms in approximating these things. Okay, so this is, these are useful things to keep in mind, that sine x is approximated by x and tangent x also is approximated by x around the origin. Cosine is approximated by a straight line around 0. Let us look at this function kth root of 1 plus x. So let's see how it works. So this is another thing we are expected to do in all sections. So f of x is equal to 1 plus x to the power k. K is a fixed positive integer. Okay. What is linearization? of f around x equals 0. Okay? So the procedure is, again, mechanical. You calculate f of 0, which is 1. Now you calculate the derivative at a general point. This is k times 1 plus x k minus 1. Now you evaluate this derivative at the given point. In our case, that point is 0, so this is k. Okay? So linearization, then linearization is slope is k, x minus this point 0, this point 0, so x plus the value at that point 1. Okay, so the function is represented, the function behaves like this straight line around this point. Okay, so before we go to differentials, because differentials are not that much important in the context of calculus. So there was this section about Taylor polynomials, wherever it is here. Okay, so these are linear approximations. So now we can shift the question a little bit. We want a linear function which approximates our given function in the sense that it takes the same value at that point and it has the same derivative at that point. Okay, so this linearization answers that question, but now we'll change it. Instead of saying that the function is linear, we want it to be quadratic first, then cubic, to be of order n in general, and next semester we'll make n infinite. Okay, so Taylor polynomials. Okay, so our first question was the following. Find a linear equation Lx. Okay, now let me make it Px. Okay, Lx such that. Okay, so first given y equals f of x and x sub 0 fixed, such that L of x sub 0 is equal to f of x sub 0 and L prime at x sub 0 is equal to f prime x sub 0. Okay, so this was the question that we answered. A linear equation means Lx is equal to a0 plus a1 x minus x sub 0. Okay. Now L of x sub 0 is equal to a0, so from here it must be f of x sub 0. And L prime x sub 0 is equal to a sub 0, a1, and it must be equal to f prime x sub 0. Okay, so this is how we found this. Now to make life easier, let's get rid of this x sub 0. Let's choose 0. Okay. Okay, so for laziness, set x sub 0 equal to 0. Okay, then Lx is equal to f prime 0 x plus. I want to write it the other way because when we are generalizing, we want to keep the first few terms. F of 0 plus f prime 0 x. That's the linearization. Linear approximation. Okay, now next question is instead of a linear term, next, find a quadratic polynomial Okay, let's write Px a0 plus a1x plus a2x squared such that it approximates our function in the following sense. It approximates our function in the sense that all derivatives at 0 agree. Okay, so that means, well, I put this in quotations because zeroth derivative is by convention, we agree that when we say zeroth derivative, we mean the value of the function. So that is the value of the function at 0 is the value of the polynomial, they agree. I take the derivatives, they agree. I take the second derivatives at 0, they also agree. Okay? If I take the third derivative, this function, this quadratic, the third derivative is 0. There's nothing left to differentiate. Okay? So the third derivative will not be meaningful. The third derivative of a quadratic polynomial is not meaningful to approximate anything. So this is as much as we expect from this polynomial. So let us check what happens. So this part tells us that P0 is A0. So let's put this in a box so that we can find it. This is A0. So A0 must be f of 0. Okay, so that one is okay. Let's look at the derivative. This is A1 plus 2A2x. Now I want to see this. I put 0 there, and I get A1. So this must be f prime 0. Okay. So again, we put this in a box. So far, you see that we get exactly the same thing here. For the linearization, we have this and this. So A0 is the value of the function there. A1 is the derivative of the function there. So this quadratic polynomial already gives me a linear approximation here. Now I want something extra. And for that extra, I have to define this. I have to find what this A2 must be. So I take the second derivative. The first derivative is already here. I take the second derivative. I get 2A2. 2A2. That must be equal according to my requirement. This part is my requirement. Okay, so I want a function. I want a polynomial whose derivatives agree with the derivatives of my function at that point. Okay, so this is now f double prime 0. Okay, so this tells me that A2 must be the second derivative of the function at that point divided by 2. Okay, so my quadratic is, P of x is equal to f of 0 plus f prime of 0x plus f double prime 0 divided by 2x squared. Okay, so this polynomial is a better approximation for my function. Again, at this point, we don't have the tools to check that this is a better approximation, so you have to rely on my word. So next semester we'll see that the error you make by taking this thing at a certain point is precisely equal to the third derivative evaluated at some point, but that point is unknown. So you find an upper bound for the third derivative divided by 3 something. Okay, so we'll be able to see an upper bound for the error made at a point. Okay. So that error is some number divided by n factorial. As n increases, of course, you are dividing things by larger and larger numbers, so the error becomes smaller for nice functions. Okay, so those nice functions we will call analytic functions. Okay, so let me do one more example with the quadratic to explain this too. this 2 is actually not 2, it is 2 factorial. So the next term will be third derivative divided by 3 factorial. So that's how it goes. So I'll do only the third one and write the general expected expression for the nth degree. Okay, so what about a quadratic, cubic? What about approximating y equals f of x by a cubic? Okay, so we want a cubic. F of x equals a0 plus a1x, a2 x squared plus a3 x cubed. And we want p0 to be f0, p prime 0, f prime 0, p double prime 0 equals f double prime 0, and third derivative being third derivative. Again, I don't go to the fourth derivative because fourth derivative of this is always 0, so it doesn't help us in approximating anything. So a cubic polynomial can give you only this much information, and we are forcing that information fits with our function in this manner. Okay, so we have p prime x equals a1 plus 2a2 x plus 3a3 x squared, p double prime x equals 2a2 plus, this 2 comes down, so just to see the general pattern, I'll put 2 separately, not multiply it by this x, and p3x is just this one. Observe that there is 1 here, that 1 is coming down, and you have this. Okay. Now I go to, okay, so from here, P0 is, these are all 0, A0, so A0 is equal to f of 0 as before. And this one is again the same as that part. So A1 is equal to, from here, f prime 0. Now here, again, if I put 0 here, 2a2 is equal to f double prime 0. Okay, and the third derivative is 3 factorial a3 equals f0. Okay, so our quadratic cubic polynomial x is like this, f of 0 plus f prime 0 divided by 1 factorial, okay, x. So this is actually divided by 0 factorial, but we never write it. F double prime 2 factorial x squared plus 0, 3 factorial x cubed. Okay, so this cubic polynomial approximates this. Okay, so in general, if we have such a polynomial, f0 plus f prime 0 over 1 factorial x plus, you write all of these things up to the nth derivative, 0 divided by n factorial xn, approximates our function f of x in the sense that the kth derivative at 0 is equal to n factorial over the coefficient, okay? Well, or rather, let me say the kth derivative is equal to the kth derivative of this, okay? So the coefficients are given like this. Here, k is from 0 to n. 0th derivative means that you are not taking derivative, okay? So this thing is called Taylor polynomial. Taylor polynomial of degree n around the point 0 of the function f. Okay? if instead of 0 we use x sub 0, all of these things would be replaced by x minus x sub 0. That's the only thing you do, just change coordinates. And instead of 0, you put x sub 0 here. But this is the general idea. The only reason why this is useful is that next semester we'll see Taylor's theorem, which says that px minus f of x can be bounded. There is a formula which says that this thing is bounded by that thing. So you have control over the error. For nice functions, the error goes to 0 as n goes to infinite. In which case, if the error is 0 when n goes to infinite, your function f of x is equal to this infinite sum. Okay? And you see that the first two terms is always the linearization. In all examples, the first two terms always turned out to be the linearization. Okay, so sometimes we need more terms, but in general, if these are nice functions, most of the functions we meet in calculus are nice functions. For them, the error goes to 0 in such cases. Okay, they are called analytic. So for most of the functions, sine, cosine, tangent, etc., you have such a Taylor, these are called Taylor series when you send n to infinity. Okay, so what we are doing as linearization here is just touching the tip of the iceberg. Okay, so we are just looking at the first two terms. This is a linear approximation. If you take one more term, that's a quadratic approximation, etc. Okay, so we'll see this in detail next semester. If we didn't have that error theorem, which is called the Taylor theorem, then this is a very nice idea, but okay, useless. If you don't have any control over the error you are making, then giving an approximation is meaningless. Okay, so you can approximate every number by 85. Okay, sometimes it's close approximation, sometimes a bad approximation. If we are not talking about error, then 85 approximates everything. Okay, but these things are nice in the sense that if you turn the pages to Taylor series, infinite series, there's a precise way of understanding the error. Okay, so that's about linear approximation. Let me talk about differentials a little bit. Okay, so talking about differentials in calculus is a little bit artificial, but you can still work things out. So I'll just mention a few things. Okay, so differentials. Now, actually, differentials are something that show up in geometry. You have the tangent space of a geometric object. You have functions on the tangent space. Those functions are generally called differentials, but they behave in a different way. And it turns out that if you forget about how you reach there, if you just look at the mechanism, you can talk about that. Okay, you can just multiply these things, take derivatives, etc. Okay, but there is no intuition in calculus for this thing. It's just that an algebraically convenient way. So if you have y equals f of x, then differential of y dy is defined as, for some reason, f prime x dx. Okay, you take the derivative of this with respect to x, and you have this. Okay, so we use it in calculus as follows. For example, this is always the formula given. So say volume of a sphere is equal to, what was that, 4 over 3 pi r cube. So here, v and r are functions of some other parameter, say t generally. Then take differentials of both sides. With respect to t. Okay, so here we are taking differential of y with respect to x, differential of y with respect to x. Okay, then dv is equal to 4 pi r square dr. And dr is r prime. Okay, so this is 4 pi r square r prime dt. Okay, so you either stop here or you go to here to check how the volume is changing when r is changing. So for example, if we are here, we can, you see these are all artificial games, so I'm trying to invent something. So if you look at only this much, okay, so this says that if r changes a little bit, then you must multiply it by this much to calculate how much volume is changing. Okay? Divide both sides by volume, but you divide this by volume, you divide this side by 4 over 3 pi r cubed. So dv over v is equal to 4 pi r3. So I think we have 3 drr. Okay, am I dividing this correctly? 4 pi's cancel, 3 comes up, r square r cube. I have this one. Okay, then you force yourself to interpret this thing. Okay, so this is the relative error, or rather relative increase in the volume. Okay, volume, you can, one way to artificially interpret differential is delta v. Okay, so how much v changes when you change the parameter a little bit. Okay, so the change compared to the total number is given by this thing. So if you change r a little bit, the volume changes 3 times. Okay, so that's the interpretation of this in calculus. Okay, so sometimes a function has sometimes a function has 2 variables in it. Okay, so for example, let's give another thing. Volume of a cone. Okay, so let's draw a picture. We like upside down cones in calculus, so we write it this way. So volume is equal to 1 over 3 pi r square h. Okay, you take the differential of this for some strange reason. Okay, so this is pi over 3. Okay, so you have 2r h dr. Okay, I'm taking the derivative with respect to this, with respect to r. So 2r h dr plus, now I take the derivative with respect to h, 1 over 3 pi r square dh. Okay, so now you manage to read this, try to make sense out of this. Again, when we look at these things, we are tempted to see dv as change in v, dr as change in r, and dh as change in h. Okay, so if you change r a little bit and h a little bit, this is how much change in r contributes to the total volume, and this is how much change in h contributes to the volume. We can play again the same game here, divide everything by v. Okay, so let's see what we get. dv over v. So 3's will cancel, pi's will cancel. I will have h will cancel. I will have dr over, and I have 2 dr over r. Okay, correct? You are checking. I'm trusting you. Okay. And now when I divide this, p r square h remains, dh over h. Okay, so you look at this thing. So if you change R a little bit, its contribution to the relative change is twice the change you are making here. If you change a little bit, it adds to the relative volume by itself, by this one. Okay, so this is another way of interpreting this one. Okay, see here, R is quadratic. So when you change R a little bit, it increases the volume more than its contribution to the increase in volume is more than the contribution of this. Okay, because the power is 2 here, power is 1 here. Okay, so well, this is forcing your way a little bit. Sometimes you use these things by saying that I'm trying to find the volume of some real life cone for some reason. Okay, when you make a measurement, of course, you are making an error, and you know how much error you are making. Okay, if you are using a meter, okay, so the line is maybe you cannot be absolutely precise about the length of anything. Okay, there's always an error, and you say probably I'm making an error plus or minus half a centimeter. Okay, so those things come here. You read this as the error. You read this as the error in your calculations. Okay, so then your volume is between this number and this number. Okay, so that's what you are trying to calculate. So I'll leave it to you as an exercise to read in the book. These are not very important. Okay, so I think we can stop here. Next hour we start the next chapter. Okay, any questions so far? Formal, informal questions?